It was a bit tricky since we had to put screenshots in between. So once we started the lab, we had to finish at the end and then put the screenshots.
Okay. So your lab reports are very much focused on running the software and basically the steps that you need to take when you're doing FEA. Do any of you know what FEA is? No. Okay, no problem, because FEA is more of a third year concept. We're just teaching you the basics. And where I can, I will try and lay the foundation for your basic understanding to then transition into third year. Okay. I realized this when I was talking about mesh sizes in the previous lab, lab 5, that a lot of people were lost when I was talking about mesh. Yes, FEA is finite element analysis. And FEA principles are what these softwares usually use. Okay, so SolidWorks, Ansys, Strand 7, they're all finite element analysis softwares. Okay, so your lab reports are broken down into the different sections that you have to cover. So you had the procedure that you followed. And when you guys write in your lab report the procedure, we don't want you to tell us like what button you clicked here, what button you clicked there, the way you went to go and change this, where you went to go and apply this. That's not what we're expecting, because the procedure is in the lab manual. What we want you to write in those steps are what was the first step that you had to do. Yes, we had to create key points, but what was the purpose of creating key points? What did we use those key points to then do later? That's what we expect when we ask you to talk about the procedure. Okay. And then the design and modeling aspects, we're expecting you guys to talk about the mesh, the importance of mesh to the accuracy of your results. So those are the kind of things that we're expecting to come in your lab report, just in case it wasn't clear enough. And when it comes to results, there are obvious outcomes for each lab, and that's where you discuss the outcomes that you're supposed to be discussing. So last week was load factors. So in the results section of your report, you're supposed to talk about the importance of load factors, what the load factor that we found was, maybe comparing our load factor to the load factor of other studies that have been done, or other analysis run by other people, if you could find that kind of information. Okay. So if you can, have a pen and paper ready, because as I go through this lab demonstration, I will be telling you exactly why are we applying this, why are we doing this, what's the purpose of this step. And you guys just take quick notes, and then you can use this to then help you write your lab report for lab 6. Okay, Payal's asking, in lab write-up format, there is a part saying modeling and or design. What are we supposed to do or show under that section? Okay, so modeling and the design is when we are basically defining the geometry. So we drew our beam, and then we apply the mesh. So that's the modeling section. And you may also talk about the boundary conditions that we apply. Boundary conditions are also known as restraints. Are you all clear as to what I mean when I say restraints? No. Okay. So a boundary condition is, okay, let's say we are looking at a truss. Okay, I'll try and draw here. You all able to see my screen? All able to see me drawing on the screen?
Yes, sir.
Okay, sorry. I'm sorry if it's going to be ugly and all, but I'm trying to draw with a mouse here. Okay, so let's look at a truss. Mangana. Oh, okay. Right. Okay, can you picture a truss? Let me try and Google a truss. Maybe that'll be better. Right. I'm just looking for an image of a truss.
Sir, just so you know, we are still at the question. We can only see the question part. But we have seen before.
Yeah, that's fine. I'm just bringing it up now.
Okay, sir.
Okay. Right. Can you see what I'm looking at now? This truss.
Yes, sir.
Okay, great. So a boundary condition is basically, say we were to apply a force, right? A force here at the top point. Okay. And we were to restrain the bottom points down here, 1, 2. Right? Imagine this is the X and Y plane. A boundary condition is if we were to apply a force here, our reactions will be in the opposite direction. Okay, you know this from all throughout this course. We've been doing reaction forces. Okay, reaction forces happen at points where the structure or the beam or whatever is restrained. Okay, if there's no restraints, it'll just flow in free space. If there's no restraints, this point force will cause this whole truss to move downwards. Okay, it's only by restraining the corners 1, 2 that this truss stays still, and we start to get some stress. Am I making sense to everybody? If we don't restrain the corners, and I'm emphasizing the word restrain, then we don't have any reaction forces, and we don't have any stresses in this truss. So when I say boundary conditions and applying restraints, that's what we're doing. We're restraining it in the Y direction. If we put reactions here and we apply a Y force here. That's what I mean when I say reactions, or not when I say restraints or boundary conditions. That's what I'm talking about. Okay, let's go back to our the question. Okay, so those are boundary conditions. So you would talk about those in your modeling section. Talk about the boundary conditions that we applied, so on and so forth. Okay, for this week's tutorial. Oh, sorry, lab. This week's lab, we're looking at a plate with a uniform distributed load on both sides. There's a slot in this plate, and we have to find the maximum stress experienced in this plate. Okay. Now, there are a few things that we will be doing, or assumptions that we'll be making with this lab simulation. Now, if you guys have your pen and paper ready, just take note, okay? First thing we're doing is we're treating this as a plane stress analysis. Okay, plane stress analysis. Meaning we're only looking in the stresses in the Y and in the X. We're only interested in the stresses in the Y and the X plane. The Z plane is the thickness of this plate. And why are we not looking at the Z plane? We're not looking at the Z plane because we're going to make the assumption that the stresses will be uniform through the thickness of the material. Is that clear to everyone? We are not doing a three-dimensional plate analysis. We're doing a plane stress analysis. So we're only looking at the X and Y components and we're making the assumption that the thickness has constant stress variation, okay? The stress through the thickness will be the same. Meaning if we look at the XY plane and we see a stress peak here, we're assuming that that stress peak is going to run all the way through the thickness. Everybody following? Okay. So that's the first assumption we're making. And why are we making that assumption? Because it will cut down on our simulation time. The more nodes you have, or the more elements you have, the longer it takes to simulate, and the more complex, the more processing power your computer needs to have, okay? For some of you, it's already struggling, just trying to open the software. If we try and run a complex simulation, your computer might just give up. So we are only running a plane stress analysis to just try and simplify our analysis, because we're making the assumption that the stress will be uniform through the thickness. Second assumption. Some of you have seen, and we've talked about it in some of our tutorials, the importance of identifying symmetry. Are you all clear as what I mean when I say symmetry? Let's take this shape, for example. We slice it down the middle. Okay? We can all see that this shape is symmetrical to this shape. Okay, so they have geometric symmetry. We can also see that the loads are applied symmetrically, okay? The same amount of load that's applied here is the same amount of a load that's applied here. Yes? If
Yes, sir.
okay, it'll be useful if you guys can like unmute your mic to respond, because as I go through the simulation, I won't have time to keep checking the chat. So if you have a question, please unmute your mic, ask, and then mute again. Okay, so we have geometric symmetry about the y-axis. This is the y-axis, okay? We also have load symmetry about the y-axis. So using that kind of observation, we can say that if we just simulate this half, and we times it by 2, or we mirror it, we'll get the results for a whole plate, right? If we were to just simulate, or we were just to model half of this shape, and then apply the boundary conditions and then load it, but at here, we apply a mirror boundary condition or a symmetrical boundary condition, it would be the same as this times 2, just flip it about the y-axis. Is it making sense? Is it making sense to everybody?
Yes, sir.
Okay, great. Okay, I just want to make sure that it's making sense. I don't want to confuse anybody along the way. Okay, so we can see that it's symmetrical about the y-axis. We can also see that it's symmetrical about the x-axis. Now this is the x-axis, okay? X. This section is symmetrical to this section, yes? The loads are the same about the x-axis, yes?
Yes.
So we can simplify our simulation even further. Instead of simulating half, or instead of simulating the whole thing, we could simulate it as half, or we could even simulate it half this way, or even better, we can simulate it by just modeling a quarter. Okay? So what we're essentially doing is, hold on. Okay, You able to see me in the camera? Right. So what we have essentially is we have a full plate and we're applying a load this side and this side. Okay, I'm making it tense. Tensile stress in the middle. What I'm saying is we could fold it in half and simulate this side pulling, and then mirror it about the y-axis so it looks like the same thing. Or we could fold it in half this way and pull it this way and mirror it about the x-axis. And when we mirror it, I mean we flip it so it looks similar to this. Or even better, we could fold it this way and then fold it this way. And now we just simulate a quarter. And if we were to mirror it about here and about here, it would be the same thing as the full shape. That's fundamentally what I mean. Okay. And that's the process that we'll be using when we go about doing our simulation. Okay?
So just a question.
Yes.
So if we are only representing the quota, the final answers, the results we'll get will be multiplied by 4.
No, because we will be applying a thing called a symmetrical boundary condition, which means the software is smart enough to already flip it and account for the other quarter.
Oh, okay, set.
Okay, so all right. So hopefully you've all opened your Ansys software. You're able to see my screen?
Yes, sir.
Okay, great. Okay, so first step, go to your preferences and set it to structural. Structural analysis, we'll click OK. Done? Everybody still opening the Ansys software, or you all with me right now?
Mine is done. I don't know about the other.
Everybody else?
I'm done.
Done.
Okay, so now we'll go up to our commands prompt /units, SI. Once you've done that, press enter.
Done.
Nice. I need you guys to let me know when you're done, so that I know when to carry moving on. Right. Next thing, a lot of people had questions about how to save. So you go to File, Save As, and you type in whatever file you want to save it as, whatever file name you want to save it as. So in this case, I will write mm211 lab 6. Okay. Before I press OK, I will go to my directories, select wherever I want to save it. So I want to save it to my desktop. Now I click OK. It'll pop up again like this. You select desktop again and OK. Everybody done that? Great. Okay.
Done.
One more time, please.
Okay. File, save as. Type in whatever name you want to save it as. So in my case, mm211 lab 6. Select desktop in the directories, then click OK. Since I've already done it just before, this will pop up. But for you guys doing it the first time, you click it once, click OK. It'll show up again like it's done nothing. You select desktop again in the directories and click OK. For you guys, when this pops up, do you want to replace? You always select yes. If not, it'll create multiple copies. And you won't remember which one you are working on currently. Okay. As well as doing that, it's always a good idea to change the job name. So we'll go to File, change job name. I want to save my job name as plane stress analysis. Okay, plate with slot. Oh, there's a word limit. Okay, I'll just save it as plate with slot. Okay. Once you change your job name, just click OK. You'll see up in the top corner that says Ansys Mechanical Utility Menu Plate with Slot now. This is your job name. This is the job that you opened. Also, you go to File, you can change the title name. Let's go Plate with Slot. Click OK. Now if we go to Plot and Replot, it'll show in the bottom corner. All right, everybody with me up to here?
Yes, sir.
Okay, great. So all we've done right now is we've just saved the file paths, changed the job name, changed the title name. Now we can start with the fun stuff, the analysis. So we'll go to preprocessor. We'll go to element type, add, edit, delete. We'll add a new element type. And this week we'll be using a new type of element. This week we'll be using a solid element. So solid on the left-hand side, and you have different options: quad 4, 8 node, quad 4 node 182, quad 8 node 183, so on and so forth. What this essentially means is it'll create a quadrilateral element, so a square element when it does its meshing. You might want to take note. It'll create a quadrilateral element when we do our meshing, but it'll only have 4 corner nodes. The difference between this and the 8 node is there will be a midpoint node on each of those squares. So we select quad 4 node and click OK. So we have created our new element. Now we go to options and we just make sure that our K3, our element behavior, is set to plane stress. Okay. By default, it'll be in plane stress, but just go and make sure, just to be on the safe side. We'll click OK. With all that done, we can close. And now we've successfully defined our element. Everybody okay up to here?
Yes, sir.
Everybody else?
So once again, please.
Element, okay. Element type, add, edit, delete. So I'll just delete this one. Go to add, solid on the left-hand side, and the first option, quad 4 on the right-hand side. Once that's done, you click OK. Now to make sure that we have the plane stress setting on, we go to options, make sure it's set to plane stress. By default, it'll be in plane stress. We click OK and close. Okay, next thing to do is we define our material properties. So material props, material models. Now on the right-hand side, structural, linear, elastic, isotropic. For our Young's modulus, according to our handout, it's 200 gigapascals. Poisson's ratio is 0.3. Click OK. And we can just exit this dialog box. Okay. Right. So now we can start doing the modeling.
So one more time, please.
Material properties. Okay. Material props. Material models. Structural, linear, elastic, isotropic. Type in the Young's modulus, so EX 200, E9, and in the Poisson's ratio, or PRXY, 0.3. Once we've done that, we click OK and close the material behavior dialog box. Set?
Done.
Nice. Okay. So the next step, we start to do our modeling. We go to modeling, create, key points, inactive CS, inactive coordinate system. Now the key points are given in your lab handout. So please refer to your lab handout. Key point 1, there are only X and Y coordinates because we're doing only X and Y. We're only looking at the XY plane because it's a plane stress analysis. So coordinate X, 0.02, 0. In between applying key points, click apply, not OK. Apply. And do the same for all your key points. So key point 2, 0.06, 0. Apply. Key point 3, 0.06 and negative 0.06. Apply. Key point 4 is 0, negative 0.06. Apply. Key point 5 is 0, negative 0.04. 6 is 0.02, negative 0.02. And our last key point 7, is 0 and negative 0.02. I click OK. When we reach the last one, we click OK. You should now have 7 key points on your screen. Everybody have this?
So still.
Okay, sure. No worries. This session will end in 3 minutes, so I'll start a new chat room and post it to the Viber discussion forum for 211, okay? I'll put the link in the Viber chat. Okay, guys?
Yes, I got it.
So I'll just end this session now and then create a new one right after this.